Welcome to the last lecture of this semester on motor control. So, motor control. The word as such, I think this term is really more common in human movement, where people talk about motor control and how we, the peripherally, physically bring about the movement of the arm. In robotics, people don't really use that term. They talk about control, and we'll have a look at that. And that entails also really the physics and dynamics of the plant, as the engineers say, of the arm itself. And I will be teaching a little bit about that today as well as control principles. So I really talk about robotic control, but I use that term because I think it's a very nice term, because what you will see is that the physics of the arm also contribute to control. But this lecture is really very classical. In fact, I'm following, I think part of my slides are sort of inspired by pages of this Lynch and Park book, Lynch and Park, which I might have referred to earlier, is available online, a free version. It's not exactly the printed version, but it's very close to that. I personally also love this book, which I might have referred to earlier. It's more mathematical, but also very clear. And there's also a legally available online version now available if you search it on the internet. Both very good books. This is more elementary than that. So the Lincoln Park book is a really good book if you want to know the principles of conventional robotics. So this is robotic arms and their control and planning and all that, not for autonomous robotics, really for conventional robotics. So this lecture gives you, in a sense, a little bit more, it's like a 1 hour summary of the sort of things that usually are a whole course in robotic arm control. So it's more about getting the flavor of that right and so on. So it's maybe culturally enlarging or inspiring lecture. In autonomous robotics, when you really want to control arms, these problems are relevant. And in human motor control, the sort of things that Lei Zhang presented to you, that's very important, because actually in human arms, the control is very tightly connected to the actual dynamics of the arms, because muscles are so weak. They have to take into account interaction torques and resistance, inertia, and all these things. Good. So that's a little bit of motivation. So just let's start with the physics, mechanics. Newton's law, right? You're all familiar with that, I suppose, from high school, I suppose. So essentially says that when you have a mass m and you describe its spatial configuration in an inertial frame by x, this would be a vector in general, a three-dimensional vector. Then this is the law of motion, that is the acceleration of that mass times its mass, which acts as inertia, is zero unless an external force acts on it. Right? It being zero, that's this principle that the state of a moving system, its position and velocity, its velocity stays constant, and therefore you can predict its position when there are no forces acting on it. And then the concept of force is exactly the thing that changes the velocity by accelerating. In robotics, non-inertial frames are common. So rotating frames are not inertial frames, right? And you know that what we call centrifugal force, it's apparent force, the fact that then in a rotating frame, the velocity does not stay constant. We would say, the centrifugal force drives a particle out of a rotating frame. And the centripetal force is this hypothetical force that would keep the particle from that. That reflects that the laws of motion are different there. And the other aspect of the Coriolis forces, also an apparent force, is really just due to the fact that the frame is not inertial. I don't know if you all have an intuition from that, maybe from high school. For instance, a very good way to think about it is if you have a carousel that is rotating, let's say it's a plane, and now you're shooting a ball from outside the carousel across that carousel. Let's say there's no friction, and that ball would be just going straight, of course, in the outer frame. But if you're rotating in the carousel and sitting on that, and you're watching where that ball is in the carousel, then you can perhaps imagine that it would make a curved trajectory within your carousel frame. I can imagine that as you're rotating the ball, moving along this outer line, is a different path. And that apparent force that would explain that discrepancy is the Coriolis force. And you will see in arms that plays a role because robotic arms consist of rotating things, right? And they're also, of course, often accelerating. I mean, there's acceleration in the rotation, right? That reflects the centrifugal force, and then you would actually accelerate frames as well when you move an robotic arm. So robotic arms are built of rigid bodies. An individual rigid body is I thought I had a slide of that here. No, original rigid body is a piece of mass that has some spatial shape that is constant. So each of these elements would be a rigid body. And for a rigid body like that, you have really 6 degrees of freedom. So 6 initial conditions that you can vary in position space. There's actually 12 numbers you can vary. You can vary the corresponding velocities or momenta as well. So the 6 are the spatial position of the rigid body, x, y, z, and the orientation along sort of 6 possible axes along which could rotate these frames of reference, the rigid body. And so one rigid body has 6 degrees of freedom. So you fix 6 things to configure, to determine its configuration. And if it's a moving, a mass under some external force, then we would say it is, you can also fix the 6 initial velocities. Now, this is being Newton's equation being a second order differential equation means you give as initial condition both position and velocity. And there are other formulations, we'll get to one later, that transform that into, for instance, position and momentum. So each individual rigid body has the 6 degrees of freedom. And then in robotics, we're talking about constraining these degrees of freedom by establishing links between the joints, between the segments. So for instance, this would be one segment of the arm, and there would be a prismatic joint here. That is a hinge joint where you could only rotate around one axis. And then that radically reduces the degrees of freedom in this second segment, right? This first segment could be, actually this segment is supposed to be also mounted on the ground on some base through a prismatic joint. So it also only rotates around this axis. So this is like looking an axis that goes here through the visual plane that you're seeing. And so radically reducing the degrees of freedom, because now you can only rotate this segment around that axis. So it's fixed in space because this axis is mounted on a table, let's say. So XYZ is fixed, and the orientation along this axis and the depth axis is fixed, and there's only one rotational degree of freedom left, and then another one for this one. So this whole system would have only 2 degrees of freedom. And again, you would have the velocities as the second variable for each of those. So if four numbers you fix, or 2 positional numbers you can fix to determine its configuration, even though as 2 rigid bodies, it would a priori have 12 such degrees of freedom, 6 plus 6, right? So you can see it's a very strong reduction in dimensionality. You can perhaps get a first sense for how complicated it would be to use the classical Newtonian picture for that kind of dynamics, because now you would have an equation of this sort of nature for all the degrees of freedom, and you would have to capture the constraints by some functions that express that certain relationships are constant. There would be then 10 such equations because you have 12 degrees of freedom minus 2. And here I didn't even reflect that these equations, these would be the translational equations, but the rotational equations involve inertial moments and torques. So it's you'd have to find the right reference frame for those. So it's pretty hellishly complicated to describe rigid bodies like that in Newtonian dynamics. And I'll show you in a moment how we really do that, which takes place in the framework of Lagrange, the Lagrange approach, Lagrange equations. And the Lagrange equations are based on these ideas of generalized coordinates. So in Newton's law, you have a physical principle of what are the right variables. It's really position and velocity, or position and momenta, degrees of freedom of rigid bodies, of masses. And while the Lagrangian approach says I can just introduce some number that I call generalized coordinate that somehow captures the degree of freedom that is given a value of that number. The underlying physical degree of freedom is well defined. And so you can see here, it's very easy. You could just take these joint angles, right? This angle against some arbitrary axis, and then this angle against the previous segment. These two angles very conveniently describe the configuration. And then I would write down an equation that already from the very beginning only has as many degrees variables here as there are actual degrees of freedom. And therefore I get rid of all these other constraint equations. And that's the framework that we use in robotics. So there are three frameworks in mechanics for those who are interested in that. So the classical Newtonian is what you learn in high school, is very rarely used. Lagrange, which I'll explain now, and then the Hamiltonian framework, which is used in a lot of other contexts, and actually quantum mechanics is a generalization of the Hamiltonian framework. So the Lagrangian framework is based essentially on this function, the so-called Lagrange function, which is a really somewhat odd initially. It's the kinetic energy of your system that depends on the generalized coordinates minus the potential energy. The Hamiltonian is where there would be a plus. So Hamiltonian is much more intuitive, perhaps. There, the function from which you derive everything is the energy of the system, right? And conservation of energy, see, get its constraints from that. Lagrangian, it's the difference between these two. So I'll illustrate that in more detail later. And the key insight is the famous principle of least action. That is, it's a physical law that was discovered. You could say it's an axiom, and everything else, then everything derived from that provides evidence for that axiom. It says that the action, which is really just the integral in time over the Jacobian, this is the action A. And the least action principle is to say that the trajectories q of t and q dot of t that a physical mechanical system described by these generalized coordinates will realize is the time course that minimizes this integral. So it minimizes the integral over the Lagrangian. Again, that's the difference between kinetic and potential energy. That least action principle, there are whole books about that, it's a kind of real magic. That is also generalized in an interesting way in quantum mechanics. Some of you might know that leads to the path integral, where you say they're all possible paths, and each possible path has a probability that is proportional to exponential of minus the action with some other terms in there. And so that just, it's not just one particular path, but there are many possible paths, trajectories, and some of those trajectories are less likely than others, and it's the action that determines how likely they are. So that's just an axiom, you could say, or a law of nature. So this is another, rather than just postulate Newton's law, this would be an alternative postulate, where you just claim that, and then you can derive something like Newton's law. In fact, I will derive roughly the Euler-Lagrange, the Lagrange equation, or Lagrange equation of motion, which is the Euler-Lagrange equation of that variational problem. Euler-Lagrange is actually a general method of solving constraint equations where you minimize something. It's very easy, but just a rough idea. Just very, very easy if you accept working somewhat freely with these variational principles. You probably don't know variational calculus, really, technically speaking, but it's very intuitive. So when we want to take the variation of something, we can do that sort of like a derivative. So we can take the derivative of A with respect to Q. It's actually the derivative with respect to a whole function. That's called a variation. But you can sort of say it's intuitive, like a derivative. So if I want to compute the derivative of this integral, I have to take the derivative with respect to the free functions in there. So there's Q in there as a function and Q dot as a function. So this is these are the partial derivatives. So I take the dl d by dq. Here it's really the dependence locally for any value of q times the variation of that trajectory q, plus the derivative with respect to q dot, and then the variation with respect to the derivative of q times dt. And here you need to believe now for now that the variation of velocity is the same as the actually I just expressed here what the contents of that is, and you can exchange the variation with a d, and now you can do a partial integral of that. That is, you lift partial integration, right? You lift this here up by integrating this one here. That would be the term that's evaluated at the boundaries, and then you take the derivative of this one with respect to the derivative in time of the other argument. This one here, the derivative in time of that will be this element, and that's what we start with. So put that on the other side of the equation, then you get this here for the right-hand side of this equation by partial integration. You can try that maybe at home to reproduce that, where you treat the variation just like a derivative. And the first term is evaluated at the boundaries of that integral, and the boundaries of that integral would be the trajectory from one start point to some endpoint that you're looking at. And the principal action, this action principle says that the trajectory that goes from initial to a final condition is the one that minimizes that action, and therefore the initial and final condition is fixed. There's no variation there, so this term is 0. So you only have that integral being 0, and then there's always the logic that this is the variation of the function, so any possible change of the function q of t, and for something like that to be true for any such change, this thing has to be 0. The parenthesis has to be 0. If it was, if it wasn't 0, then it would only be true for certain specific functions that this integral is 0. So you derive that this term here in the parenthesis is 0, and that is the Euler-Lagrange equation. Oops, sorry. So the equation of motion, in other words, of the Euler.
I have a question.
Yes, please.
So here we have a minus between the kinetic and the potential energy. So if we had
inside the L. Mm-hmm.
Yes. So if we had a plus between that, we would only be able to minimize this equation. But because of the minus, we can set this equal to 0, and then we find a solution.
That's sort of a misunderstanding. So when the Lagrange equation function where you have that minus, that's where the integral over that's the action that is minimized, and that leads to this equation, right? It's a different a question of how you would get the equation of motion from the energy. So when you use the Hamiltonian framework, the principle of how you find the equation of motion, the Hamilton equations, is a different one. It's unrelated in a sense. So there is no cheap trick of how to say I could just substitute the Lagrange function by the Hamilton function. It's not an obvious connection. So this is just magic. You have to just believe the principle of least action, and then you will get that equation. So here it's inside the L that this exchange. Maybe when we come to the example, you see maybe more intuitively why this could be true, but it is really just the law of nature. It just happens to be true. There's no direct way how you can derive it from something else rather than just that action of least action. I don't know, this probably doesn't answer your question probably. Does it?
Not really, but I'm looking forward to see an example.
Okay, good.
Maybe I will get it then.
Yeah. Good. So this is the Lagrange equation of motion. So this replaces the Newton's equation of motion. I didn't explain how you get something like forces, right? In this framework, forces don't really play a role, but there is a way of talking about generalized external forces, which I'm not explaining, and that would be things that end up here at this level. So this is just the writing it with indices, but this is the equation. So you will often you find this index version. It's useful because these Q are just a collection of these generalized variables, for instance, many joint variables. They're not really vectors in the sense of a vector space, don't have a scalar product and so on. So it's really not quite right to think of this as a vector valued equation. It's really just a short for this here, for many of these individual variables having this kind of equation. So these would be the generalized torques actually in our cases. Every formulation you have, depending on your physical, the variables that you're using is Q, this has different meaning. We'll have to look at that. So some of those of you who've had that in, I don't know where, in undergraduate physics or something, that you would recognize that that's the equation that's often being used. So what I want to illustrate to you now is how that helps you to derive the equations of motion of robotic actuators, and they have a certain reliable form that's always the same. And then you can interpret the terms in these equations, and that is helpful to understand some of the problems of control without having to understand the details. So again, this is sort of axiomatic. That is, we're just saying that is, this kind of equation is the equation of motion of rigid bodies that have constraints. So let's take the simplest example would be a pendulum, a free 3D pendulum. Right? So there's a point mass. We assume that under gravity is pulled down, and it is connected to with a length L to a rigid cable attached to an inertial frame, so it can swing and oscillate. It has 2 degrees of freedom left, namely it can rotate, around in a plane. The stator would be in a plane along the up and down in the vertical, or it could rotate. It's sort of a degree of its projection onto a plane that is parallel to gravity. That will be the one is called the azimuth, and the other, I forgot the English word for that. So these two generalized coordinates would describe that pendulum quite well. This, yeah, so just 2 numbers. I'll come back to that later. So the kinetic energy of that is easy to compute, right? That is really just the velocity times 1/2 mass velocity squared, and the velocity is why is it actually r, but it's r dot. Actually, I didn't quite do that right. So this would be the velocity. Quite a lot. I have to compute the velocity of this here in, so let's say it rotates here. I'm not quite sure actually what the r dot here is supposed to mean, but you could compute the velocity if you have some velocity theta dot, then the velocity of this element in outer space would be, proportional to the length, and along this it would be really just theta dot. So the linear velocity would be L times theta dot, and then in this plane you would have to look at the effective radius, right? This distance here, that would be 1 minus cosinus theta. Actually, it's actually sinus squared theta, and then that can be written this way, and then the velocity would be proportional to theta dot, and then these are the velocities squared here, and so 1/2 m times velocity squared is the kinetic energy, and the potential energy is just a question of how elevated this here is. So you have to compute that elevation relative to some arbitrary 0, and that elevation is proportional to the cosine theta, right? So if theta is really large, that will be the maximum value. When it's here up here, that will be 1, and if it's hanging down, then you have the lowest potential energy because it's lowest in the gravitational field. So these are relatively easy to derive. I didn't now do a very clean job, but you could certainly figure out just computing with these variables what any velocity of this mass squared is, and then it's for this, and then the potential energy likewise. And so the Hamiltonian is just taking the difference between these terms, and that will be this expression, right? And then you take the equation of motion, you just take the derivative. So we're just inserting into the equation the Jacobian, very mechanical kind of computation. We'll go through the details of that, just derive all that, and then you end up with 2 equations, right? It's the derivative with respect to theta and with respect to phi, and these are written here in vector form. This is the first equation from the derivative with respect to theta and the second with respect to phi. And you find there are two second order terms here from this derivative here and here. And then you sort them by theta dot, and those are the ones that don't contain any theta or phi dot. So you see this will be the angular acceleration, but in these funny two different variables, right? It doesn't have any direct physical meaning. And the matrix in front of that, that would be what is called the inertial matrix. And then there are terms that have both theta and phi, actually only theta configuration of variables, but also velocity variables like phi dot and theta dot. Those contain all the so-called interaction torques. So here it's only centrifugal or centripetal forces. In general, there would be also Coriolis forces in here, which don't show up in the simplest case. And then you have a term that only depends on the giant angle configuration. That is the gravitational term. You can very clearly see that this is related to how elevated this pendulum is in gravity, that being zero. So that's the equation of motion of that pendulum. So the physical interpretation, what one of you asked for, essentially the idea is that when this is moving very fast, so high kinetic energy, that will be where it has peak velocity, you know, like it goes through the, if this would be swinging, right? When it goes through the minimum, that's where you have peak velocity and you have minimal potential energy, and where you would have minimal potential energy, this will be at the turning run. Let's say it just works along a plane. Let's neglect this rotation, which has actually constant energy. Will be just going up and down. And then at the turning point, the velocity would be minimal, would be even zero if there's no rotation in the plane. And it would be purely potential energy. And then at the minimum, when it goes to the minimum point, it would have the maximum velocity. And so the Lagrangian somehow captures this interchange between kinetic and potential energy. So you could think of the equation of motion as saying that that exchange is preserved. So you're over the course of the motion, you're not you're changing kinetic energy only by inserting it into potential energy and vice versa. So that's some form of energy conservation that leads to that. I know, maybe that is somewhat intuitive. I don't know. So, of course, I can't really give a whole introduction to mechanics in such a short time, but that's sort of the idea. I don't know. Yeah, for the exam, I wouldn't even ask you really about this. This is more really cultural background. I'm not going to ask you to give me answers in. So the kind of things from this lecture, maybe this intuition that robotic arms with these joints don't reduce the degrees of freedom, to understand what a degree of freedom really is physically, the initial conditions you can give, maybe that there are two variables of position and velocity. Not anything more than that, please. This is really just for fun. Okay. Good. Okay, here a robotic example. Again, so one message of this is that even though you maybe weren't able to follow in detail, it's relatively straightforward to do this computation. Well, if you were to take Newton's equation for this is hell. It's very difficult to do with Newton's equations, right? So this is very powerful in the Lagrange formulation. That's how historically it was. This is 200 years old, right? But it is still very powerful. So typical robotic example in 1D, just to make it simple, right? The example I showed initially, and you have now these rigid bodies, right? And again, it is actually relatively straightforward to kind of guess what the kinetic energy of those things would be and what the potential energy of those things would be. So the kinetic energy, for instance, really just these velocities, and you'd have to think of the velocity of the center of mass of these segments and then the rotational velocity. So this is the rotational kinetic energy, which is proportional to the squares of the rotation here. And you have to know it doesn't matter around which axis you're looking at that. And then this is the kinetic, the linear velocity of these elements. And there is, you have to take into account that this whole body is also transported by being attached to that. That leads to this term. So after some gymnastics, you find it looks like this. And then this is the notation often used in this field where C and S are used as short for sine and cosine. And the potential energy I didn't write down, but you can see it's very easy to see that it's just a question of how elevated the center of mass of each of those points is over the ground or some arbitrary fixed ground. So you have to compute this elevation and that elevation, simple functions of theta and theta 1, theta 2. And then if you again take the derivatives, put this all into this machine, then you get out this complicated looking equation, right? There are cosine functions in here and sine functions, so it's even more complicated than it looks here. But it has that same structure. So it has terms in front of the two accelerations, a matrix. We would call that the inertial matrix, right? That term, that is very large, then at the same external torque that you put in here, you would get smaller accelerations, so the inert system, and where it's not so large, you get more acceleration for the same torque. And then here the term that has the velocity in here has a matrix in front that combines again centrifugal, in this case also Coriolis forces. And there's no actually, sorry, there wasn't actually any gravitational, because I was assuming this was in this plane. So I can write it down for gravitation as well, but this was a planar. Gravitation is vertical to this axis, so constant potential energy. And they use, I didn't tell how these external things, these generalized forces come about. They are then the active torques. And that's the equation of motion we'll see all over the place. I wrote this down here in general form. So the general equation for the open chain manipulator has always this form. And that form is one in which the second derivative here and the inertial moment, and then the first term, and this can also depend on velocity, and this does not actually generally depend on velocity. I'm sorry, this shouldn't be here.
I have a question referring to the last slide. So there you had the parameters beta and delta, and I don't see where they really come from.
Yes, I didn't really explain that. So they are combinations of the lengths and the masses. So
okay.
I just do this to get you a feeling for what things look like, but I didn't really derive that. So for instance, the Link Park book has that derivation. Both books actually have that derivation for the two-link planar robot arm, and you can sort of follow through that if you want. Yeah, you're right. So this is I don't want to go too deep into these things. So that's the general shape of all of these equations, but so that's good for understanding what's happening. But of course, to compute concretely these different terms, you have to use the Lagrangian framework really in detail. Now, in reality, I mean, I only did these toy examples, right? If you now do a real 3D arm, you have a much more complex mathematical representation of that. And there are different historical approaches to that. So the approach that's still being taught, I think, in sort of the mainstream approach called the Denevit-Hartenberg notation. So in that notation, you're thinking of a kinematic chain as a sequence of reference frames, and you always have to work from the base frame. The base frame is where the robot is, attached to the ground, to the earth that absorbs all energy ultimately, or all momentum, and then you attach a frame to a longer change, always to the next element. And in the Denevit-Hartenberg framework, you do that with respect to elements of the chain where there is a degree of freedom, for instance, where you have a hinge joint. So you attach the frame of reference to one end and the other side, and then the transformation between those two reference frames is what that hinge joint controls. But you also then have a transformation, for instance, from the other side of the joint, and then down the translation to the next joint that is fixed, right? If you don't have a prismatic or a what's it called, I forgot the English word for these segments, which you could make longer or shorter, let's say, and you also write that as a transformation, but it's just constant. It just shifts along the length of the segment, and so on. You go down the chain, and then one can figure out in terms of these kind of formulations what general kinetic energy terms and potential energy terms look like, and then you can sort of derive these equations. It becomes fairly complex. And so in practice, when you buy a robot arm, you get these matrices that describe the equation of motion by the manufacturer who's figured that out, and the controller will be sensitive to that. I'll show you that some of the control algorithms take into account these terms. So take into account these matrices. The more modern and mathematically more sophisticated approach uses the method of Lie groups. So the two books that I mentioned both use that framework. So that's much better in some way mathematically. And that uses the so-called exponential representation of movement. So four-dimensional matrices that represent the general motion of a rigid body as a rotation and a potential translation. And with that, you can write as a product of such exponentials the general transformation from the base frame to the true frame and vice versa. And then you can write down the differential equation, the Lagrange function in terms of those matrices. So that takes some other classical mechanics concepts that I didn't really explain, like how to do that in 3D rotations, right? How to write down the kinetic energy of that. But that is sort of textbook stuff. It's a bit complicated. If you're interested in that sort of thing, look at these two books. It's not something that you can learn in one afternoon. It's a little involved. Very elegant kind of field. I didn't want to go deeper into that. You can see how, or perhaps why. Okay, so that's one business, to have to know that equation and all the control that I'll be looking at. Not all, but many of the controllers already need to know these equations. And in human motor control, the corresponding question is, does the nervous system know the equation? That is, does it know that when you want to achieve a certain acceleration, that you have to count on other things happening, like interaction torques happening, right? Maybe I should make that idea somewhat intuitive. So what are these interaction torques? I'll make that intuitive. You see my face, right? You see my camera. So I can do something with my arms, and you will be seeing it. So for instance, when you have a 2-degree of freedom system, I take the elbow joint and the wrist joint, right? Go back a little. These are 2 degrees of freedom, let's say in a plane. And now I want to do a certain acceleration here and maybe a certain acceleration there. Let's say I want to have 0 acceleration at the wrist, so I want to move that rigidly and have some acceleration here at the elbow. Now you can see when I, let's say, accelerate the elbow in this direction, right? What happens at that direction? Well, if I keep it very floppy, I can sort of get an intuition for that, right? There will be something happening with the wrist. It would be actually, as I accelerate here, it would be falling back this way as I accelerate that way. And that will be because the reference frame in which it is residing is now accelerating. It's not a inertial frame. So if you accelerate your wrist position, then there would be some torque exerted on the hand that would make it flip back. And that would be an interaction torque, interaction between the joints, right? So some acceleration inserted into this through a torque that I apply to this joint, the elbow joint, induces some acceleration at the wrist that is reflected by a torque that, an apparent torque coming from the non-inertial frame at the wrist joint. And that torque we call interaction torque. And these terms here are really the sources of these kind of interaction torques. There's actually also a contribution here because when this matrix is not diagonal. And so that is a core problem of robotics and actually also of human motor control, that when you send some torque to any of the individual motors that drive the individual joints, these torques have consequences on other joints along the kinematic chain, where they essentially act as a perturbation. And there are essentially two approaches to that in control. One approach is to say, I don't care, I'll just insert in every joint the kind of torque I need to get the right thing happening. And the perturbations at the other joints that happen as a result from interaction torques, I will control individually. That is, there's a sensor there, and that will control. I'll show you now the concept for that, that will counteract these perturbations. That is the dominant approach in current industrial robotics. So these robot arms are huge, as you know, powerful, and a lot of that power goes into controlling against perturbations caused by its own motion, because the different joints interact. The other more intelligent thing would be to say, well, I take that into account from the very start, that because I can predict from this kind of model what kind of torques will arise, and I will modulate my torque to already anticipate that. And that is actually something that humans do. That is when I'm doing, for instance, I can make the elbow motion in keeping the wrist stable. And I'm actually not just doing that by making the wrist very stiff. I could make it very stiff by co-contracting all the muscles around it. But it actually turns out, if you look into detail, that you are not doing that. You're not only doing that, you're also really actively modulating the muscle that, for instance, flexes the wrist to counteract the extension of the wrist that will be generated by the interaction torque. And you initiate that contraction of the flexor before the physical interaction torque even takes place, because there's actually a certain delay before the muscle force is being built. You need to do that as a nervous system. So you're actually predicting that there will be that interaction torque. And that is means that the neural control of our movement is, in some sense, using models like that. Maybe it's not maybe literally the physical model. This is what people call the internal model, that there must be some prediction of what kind of perturbations will arise as a result of your own movement. Now, that is the control problem in a sense. So robotics has developed very, very good methods of control. I'll give you a rough idea of that. And there's a lot of work about how humans might do that. In robotics, these methods of control are so good that roboticists don't really need to think about the kind of movements they want to generate. They can just take an arbitrary movement plan, put it on the robot arm can realize it. While human movement, there is doubt whether we can actually do that. And that's an idea, as Lagrange showed you, that human movement actually is regular, has these regular kinematics, and we wouldn't do arbitrary movements. And part of that is we couldn't actually control arbitrary movements. We would have a hard time getting arbitrary acceleration profiles to be actually realized by our actuators. So that's a little bit background behind all of this. Okay, so I already said control, and I didn't really formally define it. So ultimately, we're talking about feedback control. So we're talking about a actuator, which would be the torque motor, let's say, on your arm, or maybe it would be the muscle in the human movement system that acts on something like the whole arm as the process. This would be true for any kind of control system. Could be it's a physical plant or something. There, your actuator might be some valve that you can change, and the process would be, I don't know, some chemical reaction. And then you would have some sensors that measure some aspect of what this physical thing does. Now, the actual output goes to the world, and you have some sensors of that. And that sensor information would be used to compare the state that you generate to some desired state that would be your plan, your control plan that goes in here. And the controller is actually the device that translates the measured discrepancy between what you want and what you get, translates that into some signal that changes what the actuator does. That's the general principle of control. So mathematically, you have a model of your plant. They call that process in some case, but often also plant. That can be typically a large differential equation, a lot of vector values here. So that would include also the physics of the actuator. could be explicitly time dependent in some cases when there's some external way of driving, like some external thing that changes. But in general, it wouldn't. For instance, you could have that there's some flow through the system in a plant. And there's one variable in here, which is the control variable. That's the variable that we'll have to find the right values for. Right? The output of that system is a function of the state. It could also be depending on other things. So that is what is, for instance, the sensors also, which be informed about, would be the outcome of this. And so the control law is a formulation in which this control signal is some function of that. And in practice, it's a function of some estimator of that, because this would be the physical output, but then you have maybe some sensory process that allow you to estimate that output, and engineers have special methods of how to optimally estimate that. And the control, the control law would be defined such that the output is approximates some desired output. That will be your control goal, to achieve that desired output. And there's a whole very good mathematical theory for how to do that. So this is a more concrete version of control for robotics. So there's actually in all of the robotics, there's this very special thing here, and I'll not go deeply into that, in that there is a other feedback loop, a fast feedback loop that controls how the electrical stuff, the signals you give to the motors and their actual force production, how that is regulated. And because that works so well, you can actually theoretically know what kind of current to send to the torque motor, to the amplifiers in front of the torque motors, to get what kind of torque. General could also be forces for linear actuators. So that a lot of the control laws that we'll see actually compute torque. So they say, I want a certain torque, because these models are based on knowing that when you have a torque, you can say there's a function that tells you what kind of voltage to send or current to send to the amplifiers of that system. And that has very strongly framed how roboticists think about control. While when you, and that's actually often used by engineers who think about human movement, but in human movement, it's actually not analogously clear. So when you have a joint with a muscle, and you can give to that joint some neural signal that goes into the muscle, that will be here this corresponding thing, then the torque that results from that is actually not uniquely determined. And it's just not clear you always get the same torque. It depends on a lot of other factors and time. And so that is a real question. If we can just say that the controller should generate some desired torque, which is trivially connected to the activation. That's a source of debate, ongoing debate actually in the motor control community. So other than this very special situation here in the middle, this is sort of a generic system, where there is the dynamics of the arm, and maybe coupled with anything in the environment would create the outcomes, and those would be sensed. And then the controller compares that to desired movement state, kinematic state, and then you derive from that. The controller determines from that input to the actuator, that this loop translates into a well-defined torque. So maybe I'll get over. So it's very, so just remember, even if you don't understand that fully, that in robotics, you can really, because of the way these motors are designed, you can say that you can think the control signal is a torque, even though what you're really doing is giving a electrical signal, a voltage to the electrical amplifiers that drive the arm. But you have a lookup table that tells you, if you want this much torque, I give this much voltage to the system. Good. So this is just translating all of those. So the control signal, in other words, in these robotic actuators, is really the desired torques that you want to generate. And you can assume that that works well. Okay, now I'll just illustrate a few control laws for you to get some sense for what happens here. So excuse me. Here's the sort of a minimal notion of what that means. So let's say you have a individual joint and you want to create some time course of that joint. So that will be the joint motion theta d of t. And what you actually get is some other time course theta of d, and that difference between those, that will be the error. And you would want to have some way of estimating that error by actually observing the real joint angle, and the physical sensors for that will be, for instance, shaft encoders. So some sensory signals that can determine where you are, where actually the robot arm is in the, around the joint. Shaft encoder, you can see it's a mechanical device that it's like often it's a little coding wheel, where on that wheel you have a little structure, and you can see where one joint is relative to the other on that coding wheel. And so when this disturbance is small, you could then derive from that disturbance in which direction to intervene. For instance, if it's positive, that would mean your joint is more, along this, whatever the direction of the definition is further than you want to be. And so you're going to insert into your control circuit a torque that goes in the opposite direction. So in the next moment in time, you would have reduced that error. Generally, the error will be a function of time. So during the movement, and you will have to, you can never define that as having a stationary error. It would always be something time varying. So you have a dynamic control law. And so the design of these kind of control laws is based on essentially linear system thinking. You approximate the whole system, the control loop and the plant, linearly around the desired state. So you linearize the whole equation, and then it would have the solutions like a harmonic oscillator. Harmonic oscillator is really the second order, 2-degree of freedom. Second order differential equation is the physical form of the equation of motion, as I showed you. And a linear second order equation is generally a forced damped harmonic oscillator. It could be have negative, theoretically negative damping if you do something stupid, and that would be really unstable. But so it's not necessarily conservative, because there could be velocity dependent contributions to the control that make it dissipative. So I have a damped kind of system. And so what you want is, of course, that it is damped, and you could have it more or less damped. So if it's under damped, then the system would be taking a couple of oscillations to then reach the target value. That is often not desired, or you only want to have mildly underdamped. If it is overdamped, it would take too long to reach such a state. That's also not desired. So often you want something that's close to critically damped, which is sort of the boundary between these two regimes. And that can be characterized in terms of the eigenvalues of that system which are complex numbers in the imaginary plane, and you can sort of control where you are there. So those of you who have heard control, you will remember that when you have a mathematical model, you can compute its roots, as they say, so the eigenvalues where they lie in the complex plane, then you can sort of control where they lie here to achieve something that you want to achieve for that control system. So here an example: if you have a mass that is can be characterized by elastic component and a viscous component. So this will be the elastic, this will be the viscous component, this will be its general equation of motion. Then you can understand how the elastic component contributes to the oscillator system, and the viscous component would be what determines in which regime you are here. And around this simple case, so a single rigid body that hinges around a particular joint, has some gravity, and then as an actuator here that can insert torques around this axis, that will be like one robotic joint where you think the previous segment is fixed. You can sort of understand how we would control it. So the equation of motion of that, in the spirit that I previously showed, would be this. So this will be the gravitational term. I would have written this as the third term previously. This is the Coriolis centrifugal term, and this is the inertial term, the external torque. And so if you, the simplest way of doing that is to have a linear controller. A linear controller would mean that you make the torque a linear function of the error itself, the rate of change of the error, or the integral over the error. So the P is for proportional control. That will be that. That is the larger your deviation, the more you create a torque that goes in the opposite direction. Will be this kind of line here, right? You have a computed deviation, and then proportional to that deviation, you're going in the correct direction. Then the differential, the D part of that controller would take the velocity of the rate of change of the error. So this is sort of anticipatory, right? If you're seeing that the rate that the error grows, then you can sort of anticipate that you have to do something more than if the error is already decreasing. So in a way, it anticipates how the error will develop. And so a PD controller is better than just a P controller. P controller will always lag behind because it is the error has already happened, and then you're counteracting it. And so you can see you're always lagging behind. The system will always be a little bit discrepant. And so that's this bottom term. And the integral control is sort of the most problematic one, mathematically speaking. What the integral controller does is that it accumulates error. And so what helps here, for instance, if there's something really missing, like for instance, there is just a load that didn't plan for, there is an extra load here that makes that the element is systematically offset from the desired state because of that load, which you didn't take into account when you designed the system. Then the error wouldn't really average in time to zero. It would, if you accumulate the error over time, it would lead to something non-zero. And then the integral controller will counteract to that it would try to get that integral to zero. So it can only also counteract systematic errors. So that's attractive in some way, because it would mean that if you have some systematic defect in your system, some unknown systematic influence, not a stochastic influence, then that would counteract that. Unfortunately, it also has some drawbacks. That's why it's somehow problematic. For instance, if there is a unexpected, let's say your arm is hindered because really the surface is not where you thought it was, and so you're not reaching the position because it is a little inside that surface, that term would keep ramping up the torque to reduce that to zero. So if the surface is something fragile, for instance, the robot arm would increase, keep increasing the force with which it presses against that surface and do something really bad, like break something. Clearly, you'd have to put some limit on that. So the integral term, you can see, is a little bit problematic. I think these are just details of that I don't want to go into. So if you want to know more about that, maybe go into this book to understand a little bit what the logic of these terms is and so on. So here are just a few terms to get intuition how you can now make more intelligent kind of controllers, where you take into account from the head that you can predict the kind of things that will happen, right? So again, when here I said feedback in the sense that this torque that you apply takes into account stuff that you have observed, error, rate of change of error, integral of error, and then you control. Yeah? So there's feeding back information that you've already observed. While a feed-forward controller would be something where you insert a torque that is based on some prediction on what you understand would happen. So, for instance, if you know the model, so you have some estimate over the interaction torques and the Coriolis torques, you could compute that if your desired acceleration and your desired velocity and desired trajectory was actually realized, then this would be the inertial term and the interaction term that you would have. So if you insert this torque into this equation, then you could see that then this term would match very much that term. And this term would match very much that term. Actually, I didn't write it as an H. Actually, presumably the H could also include, let's say, the gravitational term. Here I wrote it in that form, yes. And so if that was true, then the theta that results from that would be approximate that very simply, because the equation of motion would then be trivial for that, right? And that will not be exactly true because your model might not be perfect and your actuator might not really generate the exact torque that you're presenting here. But you would get very close to that, right? So by choosing the torque to have that form, you're essentially canceling that, right? If you write that torque here on the side, then this term is supposed to cancel that term, and this term is supposed to, cancel that term. And so in practice, you're combining these two things. So you see that will not in general work because there will be some discrepancy, and it can actually, this is an argument that around certain positions, this can really become very dramatic. Now, it's not so bad when you have a sort of a stable situation, but like an unstable situation, you could see that that could lead to some real discrepancy where small change in the actual physical state will lead to a real deviation. So what you do is combine these two. You have a forward and a feedback term. And so, for instance, here you maybe it comes into it. So what you will do is you say the torque I'm using is a torque that takes into account the prediction. So the desired torque times your model of the initial term is a contribution, and you're also predicting the interaction torques. But then you're also inserting here a desired acceleration. This is a contribution to the acceleration that is feedback. That is, here you're putting the error in, the rate of change, and the integral of the error. Right? This is actually called inverse dynamics, even though it looks like it's a forward model. The inverse dynamics consists of inserting a active torque that is proportional to the kind of terms that you have in the equation so that they cancel. What's called computed torque controller. And that is something that is being done on, there are robot arms that really realize that kind of system. So actually, yeah. So far I just talked about single joint, and then this was also just single joint, and so the multi-joint version is really where this is a vector valued equation. So all of what I'm writing here is the same sort of thing now for a vector valued equation, where you again would have your forward term, and these are the vector equation, right? And this would be your feedback term without the integral term in this case. And that leads then to correct behavior. So I don't think I need to go much deeper into that. Sometimes it's just gravity compensation. So you're only using it as a model, the gravitational term, and not all the other terms, but that's not so important. So that's a well-developed field. So people do that. It's not used in real industrial robots as much. And part of that is, you might be really surprised by that, is that these kind of control laws, let's say, for instance, which one here? For instance, this one, you can see that it's actually not computationally so simple. You have to do some, this is just written C, but it's a complicated term, right? If you imagine you have a 6-degree of freedom arm, it's this huge matrix that has a lot of nonlinear terms, sinus, cosine, and so on, and this too. And these are all, so you have to compute all of that in real time. At every moment in time, that matrix will be different. You have to compute it afresh at every moment in time. Let's say at a rate of 500 hertz. So you have 2 milliseconds to make the computation, and actually less than that because you also have to implement it. So it's quite computationally demanding. So even to this day, this is not something that can easily be done on a little chip in the arm, even though we are getting there. And so for a long time, this was a real constraint on actually implementing things like that, where you compute, solve these matrix multiplications that are implied in here in real time to do all of that. And that is becoming less of a problem, but simple controls like this, or even less, even just a straightforward, this one here where there is no model, so it's just feedback. that is works very well. So this one of the problems. Sensors are good, the motors are very good, and it is the technology of doing that in network and doing all these updates fast is good. So these things work pretty well. So a lot of robot arms only do that to this day. One area where these computed torque controls with inverse dynamics are really important are the special cases I mentioned already, space robotics, when you have an arm on the space shuttle. And that's a case where to have a lot of forces or torques generated just to control, like you do something here and you have to stabilize the arm by injecting corrections here, is really bad because it makes the spaceship wobble, because all the momentum has to go someplace. And that's the case where all the sophisticated versions were done. Also, the robot arms move very slowly in these cases. But other than that, there aren't really that many uses of these advanced concepts. The major problem, where there's a lot of research in conventional robotics, is to deal with contact forces. So currently, when robots actually have mechanical interaction with something, then only very crude things are done. A lot of the robots actually just paint, where there's pretty much no physical interactions, or some spraying, or they do this point welding, where you just have to hold the arm in a certain position, a certain distance, but no physical contact, right? And then you have this electrical spark going that makes the welding action. And then there are some positioning robots, and that's usually based on having a special grip point that's prepared for that action. And so something clicks close and so on. So you have to just get close enough, and then there is some mechanism that clicks, makes a connection, and that is not controlled. That's just something that has a stable mechanical state by having some click. And I mentioned, I think, in one lecture that in space robotics, there was this famous thing that humans were doing this compliant little nudging of the object into the register. So, for instance, a thing like what in German is called fräsen, and the English term for which I did know at one point. So where you're applying a tool to the surface to transmit a well-defined amount of mechanical force, or to scratch the surface, or to I don't remember that term now, to mechanically transform the surface. Those things are not routinely done by robots. Those are done by special purpose machines, which are mechanically stabilized, a Fräser in German, or various kinds of transformation machines. And they're not done by robots because robots are really quite bad at that. They can become unstable when there is a mechanical interaction with the surface. And that's something we humans are very good at, right? You can polish something, or you can use some abrasive material to clean and so on. And that is something that is still not very well done by robots. And so there's a lot of research going into that. And some of that research is actually inspired by human movement. So for instance, it's a notion of impedance, which really means that you're not just controlling position, velocity, and acceleration, but you're controlling something like the force transmitted. So you want your interaction with the object to be such that your robot arm forms essentially as a mass spring system. So it transmits an amount of force to the surface that is proportional to some distance from the surface, and maybe also to the velocity of that. So it behaves like a spring with a well-defined stiffness. And when you have that, then you can sort of think of, given how fragile the object is, let's say, I know how stiff I should make my interaction with that object, so that with the kind of precision I will get, the forces will not exceed a certain maximum force. And you better get some damping into that. So the viscosity type term is also necessary. And you saw from Lei Zhang's lecture that human muscles can be characterized like that. They are essentially mass spring kind of systems. And as a human, you can actually modulate the impedance, or the roughly speaking, the stiffness. Impedance would be the more general description, which includes the viscosity. You control the stiffness of your system. For instance, when you do karate, let's say, then you really generate a muscular activation pattern that makes your effector quite stiff, resisting change a lot. While if you, like for instance, work with tissue, right? When you fold a shirt, then you will make your system quite non-stiff so that you would be adaptive to any small change of the tissue. And for instance, handling tissue is something that robots do very badly, and therefore the industry that about sewing, for instance, the clothing industry is using robotics only in special cases, not in the mainstream. Yeah, so that's a research frontier, and it's a very interesting topic. I have last few slides that are really just sort of to point you to different directions. Just want to make you aware that the robotic equations are all about the actuator, right? The joint space description, and you're inserting torques into the joint space. So that's where the robot can be controlled. But the tasks that you want to achieve for the robot are actually in end effector space, because you want to have that tool, and you want that tool to have a well-defined velocity in the world. And maybe you have now this idea of giving the tool a certain stiffness. And so that's not exactly the same as the stiffness that you're using in your joints. And so there is a famous work by someone called Osama Khatib, who also invented the potential field approach, the same guy, who made a general framework how to do that. That is, he showed how you can write down something like the equation of motion in end effector space. This is for non-redundant arms. So it's a one-to-one mapping for these two. And then you can essentially compute, if you want to have a certain force in end effector space, like pressing against a tool, with a tool against an object with a defined force, you can then compute what would be the kind of torque vector you have to apply to your robot arm to achieve that force. And someone like Hogan, for instance, thought about how to do that such that what torque would actually create a particular mass spring coupling at the end effector level, so the tool level, to the environment. And again, a lot of these things are done academically, but in practice, there is still limited what can actually be done. So this I already mentioned. So I think I want to skip over these more advanced topics. So maybe a last little pointer is this notion of optimal control. So there is in optimal control looks more, it's a movement as a whole. That is, you want to achieve a transformation of the system from some initial state to some target state. And in a way that contains some planning, because you could also say, well, maybe I'll make a plan how to move from here to there, but you could think of it as also as a control problem. You say, I just want to make some time course of my control signal that achieves that state. And then you could actually say, well, then I can actually find a good way to do that. And the good way would be defined by some cost function, something that, for instance, minimizes accelerations, or minimizes the energy used, or minimizes the momentum change, for instance, if you do that in the space arm. And optimal control is a field, a well-defined mathematical field that does that. It has a field that has mathematical principle of how to find the time course of your control signal that achieves that final state from your initial state with some constraints that you code into the cost function. And currently, the way a lot of people think about human motor control is to say, we have to try to find what the cost function of human movement is. And then we understand human movement, even though it's just a description. We don't understand how it's neurally done, but we understand its properties. And the particular variant that is dominant is the so-called optimal feedback control. That is where you're saying, I'm not actually just trying to derive some time course of that control signal, but I'm actually trying to derive a function of that control signal as a function of x and t, so as a real feedback control signal. And then, there's some qualitative things that you can predict from such a framework. It's a very influential framework. Unfortunately, it's also a very abstract kind of framework that doesn't really invite thinking about neural systems. And I have a slide here that summarizes the kind of questions people ask here. Now, this year, I'm not going to do another lecture on human movement. I already, Lei Zhang's lecture was essentially that. I can say that the way the robotic control is thought of is very influential on how people think about human movement, but it's not actually a good approximation, because in the human case, it is not true. So they're really there. Two things I can say. One is, it is not true that in this picture here, just a second here. In this system, it's not true that the actuator is such that you can say, if I want a certain torque, I know what signal to give to my actuator. That's approximately true for these wonderful torque motors that we have in robot arms. It is not true for muscles. So in muscles, the kind of torque it generates depends on the inner state of the muscle and the mechanical state of the plant, and on the time course, on the recent values. And the signal you inject here is actually a signal, a neural firing rate, right, from coming down the spinal cord. And there are feedback loops in the periphery that one could think of like that, which are these reflexes that Lei Zhang pointed out. But these reflexes are slow. They do not actually converge on a robustly stable physical state. So this is not a good approximation, and that has a lot of consequences. Now, that really means that you can't really abstract from your actuator. You have to take the actuator into account, the muscle dynamics, the time it takes to build muscle forces, and the properties of the muscle, and the properties of the peripheral reflex loop. You have to take that into account when you make your controller. And we claim, because of the limitations of controllers for such soft systems, even when you think about your desired behavior. So planning and control are all tied up with the actuator and the local control principles of the actuator. So that's a major difference. And the other major difference is that humans are always doing compliant control. That is, when we're interacting, and we're very good with interacting with the world, we're always interacting by modulating or by determining how stiff and viscous we are with respect to that world. So you all maybe have very intuitive, if you take your make a fragile object and you try to screw something on that object, you actually determine exactly how stiff that you make that arrangement. And something, a little accident happens is when you got that wrong, right? For instance, with a fragile object like that, I would be not very stiff, so that when there is mechanical accident, I will not destroy that object by applying too high forces to it. So when it suddenly yields, there will be a limited along that spring. The force will grow slowly as my distance varies then radically. And then when I'm, on the other hand, when I'm hammering, or when I'm making digging a hole, then I might be applying, you would say I apply much higher forces, but what you're really doing is that your position control is very stiff, so that as you dig into the material, you ramp up your force quite a lot. And so that's something we humans do all the time. Well, in robotics, it's only a very special branch. And there's some conflict between that being compliant and achieving very fast movement, because when you achieve fast movement, you want to generate strong signals down to create the forces or torques that drive your arm effectively to the target. But when you have a system where the control is not very perfect, then it is, it's difficult to send the right signal down that will really take you to target, and then also be safe. So not create forces that, if there's an unpredicted collision, for instance, break your arm. So human motor control is really quite different, and the use of these concepts in human motor control can be a little bit misleading. Good, I don't want to push this any further. I'll close the lecture here. And we're here.